At the end of the lesson, you will be able to define and calculate the magnetic flux. Now, before we start the lesson, let's define the concept flux to have better understanding of magnetic flux. Flux describes any effect that appears to pass or travel through a surface. So let's assume that these tiny particles are moving towards us at some constant speed. And the distribution of particles is illustrated here. We can clearly spot the regions which have more density and regions which have less density. Now, let's take some imaginary surface and assume that through this surface some amount of particles are passing. And if we take another region but with the same area, and at the denser region here, it is obvious that the amount of particles passing through the surface will increase. And it means that flux is related to the density of the substance. We can say flux is proportional to the density. This time we will take the regions with the same density but with increased area. It's also intuitive that the flux will increase because basically in this area a more amount of particles that passing compared to this. Hence, flux is proportional to the area of the surface. And what if I take the surface and rotate it to 90 degrees? This time flux is somewhat zero because almost no particles are able to pass through that surface. The plane and the motion of particles are parallel. And as if we rotate the surface, you see that the flux increased because the area increased. And we can state that the flux is proportional to the orientation of the surface, or the angle between the motion of particles and the plane. And with the help of this analogy, we can describe magnetic flux. Now, instead of particles, there are magnetic lines passing through the surface. So we count here number of lines or intensity of the magnetic field lines, not the number of particles. And magnetic flux can be defined as follows. Magnetic flux is the quantity of magnetic field lines that pass through a closed surface. Now let's list the conditions that change the magnitude of the magnetic flux. First of all, as an analogy with the motion of particles, magnetic flux changes with the density of the magnetic field lines. So the density of the magnetic field lines is decreased here. You see it by the illustration, and it means that the flux through this surface also will decrease. And of course, if we change the area of the magnetic flux also changes. And the angle between the plane and the magnetic field lines also affects the magnitude of magnetic flux. If the plane and the magnetic field lines are parallel, then magnetic flux through the surface is zero. And the magnetic flux is maximum when the plane is perpendicular to the magnetic field lines. Okay, now we know the factors that affect the magnetic flux. But how can we calculate the magnitude of the magnetic flux? Well, it can be found by multiplication of magnetic field strength to the area of a surface through which the magnetic field lines are passing. This is B, magnetic field strength, and this is A, area. And the flux is denoted with the Greek letter phi. This equation can be used when the plane of the surface and the magnetic field lines are perpendicular. But what about when the surface is located at some angle with the magnetic field lines? In this case, we just add to the equation the function of cosine. The cosine function is maximum when the angle is 0 degrees. It means when the plane is perpendicular. And the cosine function is 0 when the angle is 19 degrees. So it means when the plane is parallel. Note that the angle is between the normal of the surface and the magnetic field lines. And what about the unit of the magnetic flux? Well, we can find it by using the equation for the magnetic flux. Magnetic field strength is measured in Tesla and the area is measured in meters square. So the unit for the magnetic flux is Tesla times meters square. And in International System of Units, scientists give it the special name, Weber. So 1 Weber is the amount of the magnetic flux through the surface when 1 Tesla of... Before we start solving problems, it will be useful to recall the previous topic. And we know that if magnetic field lines are passing through a particular surface which has area A, the flux through this surface can be found by multiplying magnetic field strength to the area and to the angle between the normal of the plane and the magnetic field lines. So this is the first problem. We see a building, and through this building magnetic field lines of the Earth are passing, and we are asked to find the magnetic flux through the wall. So let's start by writing the givens. What we know here? We know the area of the wall. It is 15 times 8 meters square. And we know the magnetic field from the Earth. It is 3 10 minus 5 Tesla. And we're asked to find the flux through the wall. Now, let's start solving problem, and this is the equation for the magnetic flux. So here the wall is perpendicular to the magnetic field lines, and the angle between the normal of the wall and the magnetic field lines are 0, and it means cosine alpha will be 1. And this is the situation when the angle is 0 and the plane is perpendicular. And if the plane is perpendicular, then magnetic flux through the surface will be maximum, and it will be just magnetic field times to the area. And let's use the givens and calculate the flux. Magnetic field of the Earth is 3 10 minus 5 times to the area of the wall, 15 to 8. And the flux, it is 3 10 minus 5 multiplied to 120 meters square. And flux is equals to 360 10 minus 5. And we can write in this form 3.6 10 minus 3. The unit for the flux is Weber. So this is the answer. And let's move to the second problem. Here we have something like an inclined plane, a 3D object, and we are asked to find the flux through each of the sides. This object has 5 sides, so we need to find the flux through the 5 sides. Let's start by writing the givens. What we know here? We know the magnetic field, it is 1.2 Tesla, and we know the lengths of the sites. So let's start writing AC. AC length will be equal to the length which is parallel to this BD, and this is 3 meters. Also, we know the length of the AB site, and parallel to this is CD, they are equal, and this is also 3 meters. And what we know also is that CE site, the parallel to this site is DF, is equals to 4 meters. And that's it, and we're asked to find flux. So I will divide this problem into 3 sections. In first section, I will look at the sites which are parallel with the magnetic field lines. I have 3 sites which are parallel to the magnetic field lines. So let's write them down. It's triangle AEC and also the triangle BFD and the perpendicular, the parallelogram CDFE. They are all parallel to the magnetic field lines. That's why we know from the equation that if surface is parallel to the magnetic field lines, then the flux will be 0. Flux through these 3 sides must be 0. And in the second section of this problem, I will look at the surface which is perpendicular to the magnetic field lines. So I have one surface only. This is parallelogram ABDS. And this side is perpendicular to the magnetic field lines. And we know when plane is perpendicular to the magnetic field lines, we can find it just by multiplying magnetic field to the area. And now we know the magnetic field, but we don't know area. So let's find the area of this perpendicular side. So area of the parallelogram is, we just need to multiply the sides, the side AC to the AB, and 3 to 3, it's 9 meters square. So flux will be equal to magnetic field, which is 1.2 multiplied to 9, and flux is equals to 10.8 Webers. So this is the flux through the perpendicular side ABDS. And the third section, we have a plane which is at an angle with the magnetic field lines. This is the parallelogram ABFE. This is at some angle. So here I use the equation with cosine alpha. Again, I need to find the area of this parallelogram, and this is also we can find by multiplying the sides AB to the AE. And from Pythagorean theorem we can find that AE is also can be found by Pythagorean theorem. This is 3, 4, and the hypotenuse will be 5. So area of this surface is 3 to 5. 15 meters squared, and flux will be 1.2 multiplied to 15, and cosine alpha. How can we find cosine alpha? The alpha, it is between the normal and the magnetic field lines. This is the alpha. And if this is beta, this is also beta. And we can find that the sum of this angle is 90 degrees. So it means if we assume that this is 90 degrees, so sum of these two angles is also 90 degrees. So basically we need to find the cosine alpha from this triangle, and cosine alpha from this triangle will be cosine alpha will be adjacent side to the hypotenuse, adjacent to the hypotenuse. And adjacent side for the angle alpha in this triangle is 3, and dividing to the hypotenuse it's 5, so it is 0.6. And we say here 0.6. So let's multiply this 1.2 times 15 times 0.6. And if we multiply it, the answer would be also 10.8 Weber. So the flux through this surface is also 10.8, and we just could find it by deduction, because if this is ABFE plane is at an angle, then the perpendicular plane is ABDS plane. So that's why